Hey guys, and welcome back. Today we're going to be talking about inspecting a system, meaning we're going to be looking for if there's more than one solution to any one of these linear systems. So our learning target, again, we're building up to actually solving these systems of equations in two variables. In order to be successful today, you're going to be able to identify a system in two variables and identify patterns of recognizing how many solutions there are to a system. We are really going to be looking for those patterns. I'm going to actually circle that. I'm also going to write the word structure. Okay, because we're going to be looking at the structure of an equation, how it's set up, and be able to tell just by looking at an equation, or maybe simply simplifying slightly to be able to see how many solutions there are. So the key idea here says when you solve two variable systems of linear equations, you're finding intersections of lines. I'm going to highlight that because we just learned that yesterday and the day before that a solution to a system is where the two lines intersect. So that's really important. When you solve a linear system, you're finding where the two lines intersect. Solving a two variable system has three possible outcomes. Okay, and I want to circle that as well. There are three, that's a little thick, sorry. Three different possible outcomes. The first, okay, this is number one of the possible outcomes, one solution. Okay, if we look at the graph, these two lines intersect once, and it's right there. The reason this is because the slopes are different. Okay, this is a slope of 1, this is a slope of 2. We can see the slope of 1 right next to the x right there, it's invisible, and then we can see the slope of 2 right there in the equation. So really, even if we were not given this graph and we just saw the system, let me write it stacked. Okay, y equals 1x minus 1 and y equals 2x minus 3, we don't even really need to see the graph at all. If you don't have a graph in front of you, you should be able to tell if there's one solution just by the fact that the slopes are different. Okay, and I'm going to write that down. Slopes are different. Okay, that's how we're going to know if there's one solution. One solution. Okay, so you can see this visually in the graph, but you shouldn't have to graph something. You shouldn't need to see the graph in order to know if there's only one solution. The other option here is no solutions. Okay, this means that the lines are parallel. If you notice the slopes on this one, okay, I see a slope of, okay, invisible 1 and a slope of invisible 1. So it seems like the slopes are going to be the same if the lines are going to be parallel, if there's going to be no solution. Again, a solution is where the two lines intersect. So if they don't intersect, there are no solutions. So I'm going to make a note for this one. Slopes are equal, but there's one more stipulation here. If you notice what's going on in the y-intercepts, the y-intercept here is 3, the y-intercept here is 1. So we need the y-intercepts to be different in order for the lines to be parallel. And there is one more situation that I'm going to emphasize the y-intercepts as well, and you'll understand why. But I'm going to make this note. The y-intercept must be different. Okay, so that was the second of the three situations. The third is infinitely many solutions. This means that the lines are the same. What you're going to get is a system where the equations look different, but if we take a look at this equation right here, 2y equals 2x plus 4, if we divide everything that we see by 2, because all of these numbers, the 2, wanted a different color, the 2 that we see here, the 2 that we see there, and the 4 that we see there, they're all divisible by 2. And whatever you do to one side, as long as you do it to the other side, the equation is still balanced. So if we were to divide everything by 2, those 2's cancel, those 2's cancel, the 4 over 2 becomes a 2. This equation really is y equals x plus 2, which is the same as that equation right there. It's exactly the same once it's simplified. So whenever we see an equation, you should automatically want to try to simplify it to see if the equation is actually the same, so that you can say, well, there's actually infinitely many solutions, because it's kind of like if I were to graph this line. Okay, I graphed my line, but then I graphed the second line on top of it. It is intersecting everywhere. That's where the infinitely many solutions comes from. So 3 different situations here. And an easy way to remember the 3 different situations is, okay, so I'm going to write options. 1, none, or a ton. Okay, that's an easy way to remember what your 3 options are. There's either 1 solution, no solutions, or infinitely many. 1, none, or a ton. So let's take a look at the first example. It says, without graphing, decide whether the system of linear equations has 1 solution, no solutions, or infinitely many solutions. So we have about 6 different systems here, and we have to analyze whether there's 1, none, or a ton. And if you notice, some of them are not in y equals mx plus b form in order for us to tell if there's a similar slope, or an equal slope, different slopes, or the y-intercepts. So we're going to need to practice what we first learned yesterday, and that's rearranging the equation so that we see y equals mx plus b. So if you need extra space, use the back of your page or try to fit it into the notes space, but we're going to do a little bit of algebra on each one of these. So let's start with this one. Okay, we need to figure out what the y equals mx plus b's are in x equals 3 and y equals 4. Well, this one is actually in y equals mx plus b form. It would just technically be y equals 0x plus 4. Now, this situation, this is actually a vertical line, so the slope is undefined. So I'm just going to write slope is undefined. I'm just going to write und. Okay, so, and the reason it's undefined is there's no way you can possibly put that equation in y equals mx plus b because there's no y. And if you remember, if it says x equals a number, that was a vertical line through the x-axis. So technically, because one slope is 0 and one slope is undefined, that means that the slopes are different. Okay, because the slopes are different, that system has 1 solution. So I'm going to write that system in the 1 solution category. So we have x equals 3, y equals 4, and I'm going to put a fancy schmancy bracket around that because I'm going to probably write more systems in there, and that's just the one with 1 solution. So now we're going to tackle this guy right here. And we only really have one thing we need to do because the first equation, y equals 5x plus 4, that's in y equals mx plus b. But the second equation, 2y equals 10x plus 8, that one we need to get rid of this too. It's y equals mx plus b, not 2y equals mx plus b. So we need to divide everything by 2. Whatever we do to one side, we have to do the other, but we have to do it to both of the terms. We got to divide this by 2, and we have to divide that by 2. So really this equation turns into y equals 10 divided by 2 is 5, so 5x, and 8 divided by 2 is 4. Well, since everything about these two equations match, I have the slopes are equal and the y-intercepts are equal. That means they're the exact same line, and thus they have infinitely many solutions. It's a line sitting on top of itself. So I'm going to write y equals 5x plus 4, and 2y, I'm going to write the original system, y equals 10x plus 8, and I'm going to put my fancy schmancy bracket around it so I know that they're together. So now I have about 4 more systems I need to analyze here. Okay, so now I'm going to look at this one. So I have x plus y is equal to -1. Well, in order to put that into y equals mx plus b, I need to take this x and move it to the other side. It's positive, so I need to subtract it from both sides. So I have x plus y minus x is equal to -1 minus x. So I have my x's becoming 0 on the left side, and I get y is equal to, again, I'm going to switch these around so that I can see y equals mx plus b and not y equals b plus mx. So I have -x minus 1. I'm going to do the same thing to the other equation. The second equation was x plus y equals +1. So I'm going to do the exact same thing. I'm really just going to subtract x from both sides. So x plus y minus x is equal to 1 minus x. So the x's cancel. We're left with y is equal to, and again, I'm going to switch these around, -x, and then that's a +1, so +1. So now I can see the slopes are matching. They're both -1, but the y-intercepts are different. One's -1, one is +1. So since the slopes are the same, but the y-intercepts are different, that means this has no solution. The lines are going to be parallel. They're going to have the same steepness, but they're going to intersect the y-axis at 2 different points, so they're going to be running parallel to each other. So I'm going to write this in my no solution category box here. And my fancy bracket to keep them together. All right, I've got 3 more that I need to analyze. And again, feel free, use the back side of your sheet for all of this work. I do want you writing down all of this work somewhere. Okay, write it down so that you get the experience of writing it down and it makes more sense to you. So we're going to now look at this equation here. We have 2x plus 3y is equal to 6. Again, I'm going to start putting that into y equals mx plus b the same way we did the first equation. So I see I need to get this 2x to go over to the other side. So since it's positive, I need to subtract it from both sides. 2x plus 3y minus 2x is equal to 6 minus 2x. So my 2x's become 0, and I'm left with 3y is equal to, again, I'm going to switch these around so that it goes mx plus b and not b plus mx, -2x plus 6. I don't want 3y though. It's y equals mx plus b, not 3y equals mx plus b. So I need to divide by 3, but if I divide by 3 on one side, I have to divide both terms on the other side. So I end up with y equals -2 over 3x plus 6 divided by 3 is 2. Now I need to do the same thing for the other equation. So that was 8x plus 12y equals 24. So I'm going to go through this process again. 8x plus 12y minus 8x is equal to 24 minus 8x. The 8x's on the left cancel. We get 12y is equal to -8x plus 24. And then we divide by 12 for all of the terms. And our simplified version, sorry, I'm going to write it over here in this little nook. Sorry if all my work is getting crammed up. It says y equals -8 over 12 reduces down. Both of those things are divisible by 4, so that's -2 over 3x. And then 24 divided by 12 is 2. So if I compare my slopes, I have a slope of 2/3, a slope of 2/3. Okay, so same slope. And again, the same exact y-intercept. So I'm going to go to my little solution boxes here. And I'm going to write that system underneath the infinitely many solutions. Because again, if they completely match, they are the same line, and thus they have infinite solutions. So 2x plus 3y equals 6, and 8x plus 12y equals 24. Fancy bracket. Okay, I have 2 more to analyze, but hey, these ones do not require any work. They are already in y equals mx plus b. So I'm just going to compare. I've got the same slopes, but I've got different y-intercepts. That means the lines are parallel. So I'm going to write that one under no solution. Y equals 4x minus 1, and y equals 4x plus 2. Fancy bracket. Okay, got that one out of the way, and now I need to analyze one more. I see 2 different slopes, so that means I don't even care about the y-intercepts. We said the key concept was that if the slopes are different, then they intersect once. So I'm going to write that system in the one solution column. Y equals 2x plus 4, and y equals negative x plus 1. Fancy bracket. Now I would like you guys to give this a try on your U-Try. You don't have to analyze 6 different graphs like I did. That was plenty of examples for you. But I would like you to do with this system is change it into y equals mx plus b, just like we did the numerous times in the example, and then tell me whether there's one, none, or infinitely many solutions. All right, so I have a little introduction to the next example because there is an alternate way that you can tell if a system has one, none, or infinitely many solutions without changing the equation into y equals mx plus b form. So I'm going to highlight a few things on this slide because there are easy ways to be able to tell without doing all that work. It says you can also apply previous understandings of number sense when working with systems of equations. So notice in this system, it says this system has no solution because x plus y cannot equal 8 and 25 simultaneously. Let me give you an actual example of this because I know sometimes it can be hard to imagine abstract concepts like this. So let's say x was actually equal to 3 and y was equal to 5. Well, 3 plus 5 is equal to 8. 3 plus 5 cannot equal anything other than 8. Okay, it has to be 8. Okay, there is no other number that you can add 3 and 5 together and equal 8. So if I were to say 3 plus 5 equals 25, that does not make sense. Okay, it's not true in both of the equations. So my idea here is if you see the same thing on the left side, but different things on the right side, okay, so I'm going to write different and the same. If you see the same thing on the right side, but different numbers on the left side, there cannot be a solution to that. And again, keep in mind, if you end up simplifying and the 2 equations become exactly the same on both sides, that's infinitely many solutions. So we're looking out for things where it's the same on the left, different on the right, or completely the same after simplification. So let's give this a try in the second example. It says, by inspecting the equations, what can you determine about the solutions to this system? So let's make note of something here. This equation, I see a 3, a -1, and a 6. There is no number that I can divide 3, -1, and 6 by all together and still come out to a whole number. So this equation is simple. It's as simple as it's going to get. However, the 6 the -2 and the 12 can all be divided by 2. So let's actually simplify the second equation. Let's divide everything we see by 2. If you try to divide an entire equation and you divide all of its terms, you still keep the equation balanced and it's still the same equation. So let's see what this equation turns out to be. 6 divided by 2 is 3. -2 divided by 2 is -1. Okay, and actually I'm not even going to write the 1. Okay, 1s can be invisible. And then 12 divided by 2 is 6. Well, look at that. We have the exact same equation after we simplified it. So this one's going to have infinite solutions. If you simplify, and it turns out to be exactly the same thing, that is infinite solutions. If what it equaled to, if this 6 turned out to be different than this number, then you would have had no solutions because the left side said 3x minus y for both of them. So I want you guys to give this analysis a try in your U-Try.
Yeah.